Log on, tune in, find out. Another good idea from Cambridge.
I'm going to talk about moment maps for smooth Hamiltonian systems and discrete symplectic analogues.
Thank you. So I've changed the title of my talk because Reinhard Crispel told me that discrete Hamiltonian systems didn't exist. And I thought, well, he would know. And at the end, you'll see why someone would think that. But, yes, so you've just seen a great talk on moving frames. And the motivation for my current talk is comes out of results that I obtained at the end of, I just wrote a 250-some page book called The Practical Guide to the Invariant Calculus, which details quite a lot of what Evelyn was saying from the point of view of multivariable calculus and undergraduate linear algebra. So I didn't get as far as the Grosvenor bases. And instead I really gave in the premier position the frame itself that was described as the equivariant map from the space to the cross-section, from the space to the group. However, that's a digression. At the very last chapter concerns variational problems and applying the moving frame to variational problems. So the applications were you have a very high order Lagrangian which is invariant under a Lie group, and you want to, so an obvious question would be, can you write the Euler-Lagrange system directly in terms of the invariance? It's a theorem that the Euler-Lagrange system is invariant and can be written in terms of these invariants. So can you do it symbolically without doing some huge calculation and then doing this back substitution? That was one of the things that came out. And of course, because variational problems with Lie group symmetries, the key theorem is Noether's theorem, which gives you the conservation laws. And the formulae for these laws is well known in terms of the original invariance, and they're very eye-glazing. They're really colossal. I mean, just to even write down everything that you need, I think takes Peter over 10 pages or more in his book. Much less, and even more to prove them, obviously. So these were the applications I was thinking of about applying this calculus invariance that you've just seen to these high-order variational problems. So it's well known that these, if you look at the set of conservation laws as a whole, if you have an R parameter group, you have R conservation laws, that there is actually a group action that acts on those themselves. There's an induced group action on those. And so I was trying to understand all of these things in terms of this beautiful new technology that we have. And I realized at some point that the induced action on the conservation laws was exactly the same as on the moment map for the equivalent Hamiltonian system. So I wanted to understand, I just wanted to understand for my own understanding exactly what the relationship was between all of these various things. Because I was invited to a program on discrete systems, I wanted to extend it to the discrete case. And then I did show the result that I'm going to show you to a couple of people who hadn't seen it before. I would be shocked if it was new. But anyway, maybe somebody has seen it. So let's have a look. So I'm going to exhibit for you a very simple formula for the moment map. So this is for, you take a high order Lagrangian system, variational system, Euler-Lagrange equations. There is an equivalent Hamiltonian system which is symplectic, and this system will inherit the symmetries and all of the conserved quantities and so on and so forth. Using the simple formula, it's going to be easy to show properties. I'm then going to show you how the results transfer to the discrete case. And in this case, what I mean is how we get the momentum map for the discrete symplectic mapping coming from a discrete high order Lagrangian. And at the very end, I'm going to give you a little general discussion on these symplectic mappings and why Reinhard would say that they were not Hamiltonian. Okay, so let's start. So my running example is the projective SL2 action. I really like this action because it's nonlinear and because you can write, It's almost linear, but the thing is that you really can do all of the calculations that I'm going to show you almost by hand, basically. So I kind of like this. So the first thing is that I'm going to insist in this talk that all of my actions in the smooth case with smooth Lagrangians, that the independent variable is left invariant by the group action. And the reason for that is because the corresponding discrete case, you cannot put a Lie group action onto n. N doesn't vary. So it's not hard to transfer the results to this case. And in any event, you can always guarantee this by reparameterizing your problem and introducing your current independent variable as a new dependent variable. All right. So my group is SL2, so you just normally write this as 2 by 2 matrices with determinant 1. This is the action here. In fact, there are 3 inequivalent group actions of SL2 on the plane, and this is the simplest one. The chain rule induces an action on UX and UXX and forever. So this is the prolonged action that Evelyn was mentioning, and you achieve it using the chain rule. And you can see that we're looking to look at in differential invariance, and we're going to use a moving frame mechanism. You need to have this regular group action. And because it's a 3-dimensional group, I need to be in at least 3 dimensions in order to achieve this nice foliation by the orbits and the existence of a cross-section. And it turns out in this case that order 3 is as far as you need to go. So the lowest order invariant is very famous. It's been known for an enormously long time. It's the Schwarzian derivative. So you get this. So this is invariant. So what you mean is you take the prolonged group action on UXXX, you divide it by the prolonged group action on UX. So it basically means you put a G dot on it on everything. So the action on UXX squared is G dot UXX all squared, and that's how it goes. And when you do this and you simplify it, lo and behold, all of the group parameters disappear, and you're left with what you started with. So that's what a differential invariant looks like when you're dealing with the integrated group action. So the general form of invariant Lagrangian, so X is an invariant, V is an invariant, and these are all of the derivatives of V. These are all invariant, and so any Lagrangian equation, any variational problem which is invariant under this projective group action can be written in this form. So here's the Euler-Lagrange equation for this variational problem splits. The operator kind of splits in this very interesting way. So this is one of the results that I get in the end of this book. And I'm going to show you how to obtain this Euler-Lagrange thing. So basically you pretend, so of course the Euler-Lagrange equation is you have to vary U, not V. So U is the thing you're varying. So, but this baby here, this EV, is you pretend that V is the dependent variable and you obtain the Euler-Lagrange operator like that. And then you pre-operate by this. This is a very famous operator. This is one of the Hamiltonian operators for the KdV equation. And part of the theory that we developed, and in fact you'll see this I did this with Tanya, who's here, and she has a very nice poster in the poster room which explains to you where this operator comes from. And in fact it comes from the syzygy that Evelyn has just been talking about. If you introduce a new parameter as the variational parameter, then you get a syzygy between the differential invariant, the invariant, if you take du by d epsilon as your, well anyway, read the poster. You can explain the existence of this very, very, very easily. Okay, so let's look now at calculating Euler-Lagrange equations. And I really need you to not look away. The process that's on this slide is the key process, and I always keep coming back to this key process of how do we find the Euler-Lagrange equations, how do we find the conservation laws, and it turns out to be easy. So here we go. We take our U and we replace it with U plus epsilon V, so V stands for variation, here, and epsilon is just a dummy variable that I've introduced. The usual term to get from this step to this step is called the Frechet derivative. But this is all that it is. You just simply differentiate under the integral sign. So obviously I'm in a functional space where this is valid. So L is smooth and I can differentiate under the integral sign. So we get to this part here, and then all I do is integration by parts. It's just systematic integration by parts to systematically get rid of all of these derivatives off the variation. So I end up with something here in green times v, and this is a total derivative term. Now this coefficient here of my variation v, that is my Euler-Lagrange equation for L with respect to u. That's the definition of it. And the result is that if this is going to be 0 for every single variation in my interval, then it's not hard to prove that this thing here, the coefficient of v, has to be 0, because you can take variations that disappear at the ends and just have our little bump function anywhere in the middle. I'm then left with these boundary value terms. So ordinarily, the variation v has to live in the same function space as u. So if the values of u and its derivatives are fixed at the endpoints, then that's going to fix v and vx all to be 0. But if you have any kind of information about u at the end that is free, then that will introduce natural boundary conditions which can be read off from here. So the natural boundary conditions are usually embedded in as part of the variational problem, and I'll come to this point later. But more importantly, if this v is my infinitesimal that you've just seen in Evelyn's talk, if it's the infinitesimal variation, then this thing here that is my conserved quantity, where v is now the infinitesimal quantity coming from the group action. Because if my Lagrangian is invariant, this is 0. On solutions of the Euler-Lagrange equation, this is 0. And that leaves me with these endpoints, and that's got to be 0, and therefore, so this is my conserved quantity. And so you can see that the formulae for the conserved quantities simply come out of careful collection of terms from this integration by parts process. Yeah. Okay, so I've just talked about all of this, and you obtain your conserved quantities. You get one for each group parameter. The formula is well known. You can calculate them symbolically in Maple. They're hideous. They're highly recursive. You don't want to look at them ever. So I'm writing this book and I'm wanting to do some stuff. So I basically decide to see what I can see. I look at my a couple of Lagrangians invariant under my favorite SL2 action. I obtain the conserved quantities. I rewrite what I can in terms of v and its derivatives, and then I just simply wrote it in matrix form. And so this is what I obtained. So this is quasi-unbelievable. C is just a vector of constants. This thing here is, it's just something depending on u, ux, and u double x according to this scheme. And this is a vector of invariance. All right, so having just written a 250-page book, I recognize, so I just got it as a matrix in u, ux, and u triple x, but of course I recognized it. This is a very particular representation of SL2. And the miracle about this particular choice of A, B, and C is that this matrix is equivariant. So what that means is that everywhere I have a u, I put a g dot u. Everywhere I have a ux, I have a g dot ux. And everywhere I have a uxx, I put a g dot uxx according to the prolongation. And then what happens is that I can the resulting matrix, the group part factors out. So I'm left with what I'm left with what I started times another thing, depending. So I get my original matrix back times something that depends only on the group parameters. So I thought this was wonderful because one of the points about Evelyn's talk is that she avoids the calculation of the moving frame using Grosvenor bases. And it's because the calculation of the frame, to do the calculations, involves implicit function theorem, and that's why it's non-constructive, and that's why you want to avoid it. But here, Nerdist theorem has calculated for you a moving frame. for free, because this is a non-moving frame calculation. Anyway, the questions that I answered in a paper with Tanya, and that you see on her poster, is a formula for this vector invariance and how to calculate this particular representation of the SL2. Now the representation is the adjoint representation, and this of course is the representation for which the moment map for Hamiltonian systems is equivariant under, and so you see the link. Anyway, so let me just tell you a bit about what is the adjoint representation. So the adjoint representation of a Lie group, so you'd have your infinitesimal vector fields. So let's just briefly review this for this particular example. What is the infinitesimal vector fields for this Lie group? Well, this is my group action on my U. The identity element is A is 1 and B and C is 0. So you simply take, you differentiate with respect to the group parameters at the identity, and you get these infinitesimals, that's what they are, and an arbitrary one parameter group is going to be in terms of a particular, you can take arbitrary A, B and C, and so basically what you're going to get is an arbitrary linear sum of these infinitesimals, and of course we're looking now for vector fields, and that's why we've got the du there. So this thing here, this comprises the Lie algebra that comes from the Lie group from this particular action of SL2. It's a three-dimensional Lie algebra of vector fields living in the set of all vector fields. And then the induced, so we have an action of the Lie group induced on the set of these vector fields, and basically on an arbitrary, you get the induced joint action on the whole of, on any vector field at all. You just simply put a G dot everywhere. So you put a G dot in your F and a G dot on there. You have to unwind this using the chain rule, and that's what you get. And so this now defines, it's very easy to prove that this is actually a group action. And the theorem is that if you start out with something inside your Lie algebra, you remain within your Lie algebra. So this adjoint action induces an action on your three fields, on your Lie algebra. So it's much easier to calculate this action on those arbitrary constants. So let's see how that works. So remember I had a 2 alpha times u plus beta minus gamma u squared. So this is my adjoint action now. And basically if I just simply undo it all and collect terms, I end up with an induced group action on alpha, beta and gamma. The theorem guarantees that this has to happen. This is the content of the theorem, that you get an induction on the Lie algebra. And so when you write that in terms of, in matrix form, here we have the transpose of the ad of G, because I've done it on the constants, I get the transpose. So this is how you calculate this adjoint action. And for our application, we need to induce the action on the, you have to extend it, you have to do the prolonged action, you get the prolonged vector fields, but it all works exactly according to how you would think. You can only ever get that one little matrix out the front. So here it is. So what does the theorem now look like that the induced action restricts to the Lie algebra? It looks like this. If I take this matrix of infinitesimals, so this is going to be d by d g dot u with respect to a1 at the identity, and this one here is d by d a1 at the identity of g dot ux, and so on and so forth. So I have one row for every parameter, and I have one column for every variable. And basically, when you do it all, what you have is you get the induced action on the infinitesimals as functions multiplied by the inverse transpose of the transformation, the Jacobian of the transformation. And that defines you the adjoint action. And the particular result that I need is I need this matrix here. What is the action on this array of infinitesimals? So it's this matrix here, which is the adjoint thing depending only on the group parameters times the original thing times the transpose of this thing here. So that's the particular result that I'm going to use is this one here. Okay, so we're now going to move from the Lagrangian to the corresponding Hamiltonian, and I'm going to do this in a particular way because this really does reveal the essence of the whole thing. So what I'm going to do is I'm going to do a trick, which is I'm going to pretend that ux, u double x, and u triple x are new variables called v, w, and z, but I'm going to impose Lagrange multipliers. So in other words, ux is v, w is vx, z is wx, and I'm going to do it like this. And you will see why this is such a fab idea in a couple of slides. So then, of course, my Euler-Lagrange equations, I'm now going to, so I write my L as this L twiddle. This whole thing here, this sort of adjusted thing, I'm just going to call L twiddle. And I'm now going to have four Euler, that V should be a Z. I'm going to get four Euler-Lagrange equations, one for U, one for W, one for Z, one for V, according to the scheme that I showed you. And of course, the Euler-Lagrange equations for the lambda i's are simply going to be the constraints. So I get these four plus the three constraints is my Euler-Lagrange system. And you can see here that I have these equations for lambda that have a very beautiful recursive, there's kind of like a natural recurrence relation for the lambdas. So the lambda 3 is dl by dz, which was the third derivative. And then I can obtain lambda 2 in terms of dl by dw and lambda 3x, and so on. So I have this beautiful recurrence relation for lambda 3, lambda 2, lambda 1. And then when I eliminate the lambdas, I would get the original Euler-Lagrange equation. So this is just a trick. Okay, so my variables are u, v, w, and z, and my conjugate variables, and here we see that my conjugate variables are always, you always differentiate your Lagrangian with respect to the derivative. So, so this is the standard mechanism for obtaining the Hamiltonian. You write down what these conjugate variables are, and of course they're my lambdas. Ta-da! So if you like to use p's, because that's the standard thing that you see in classical mechanics books, you can swap lambda for p. But but it really is just the Lagrange multipliers is what they are. So now let's compare everything. Let's compare the conjugate variables with the expressions appearing in Noether's formula. So here it is. Here's the conserved quantity for a third order Lagrangian. And I've only got one dependent variable, and you can imagine what the general formula look like. Anyway, so here's my conjugate variable, R the Lagrange multipliers. Here's my Euler-Lagrange equations. When I unwind using the recurrence formulae, what I have to have, what these actually are, using the Euler-Lagrange equations, I get these. And lo and behold, PW is the coefficient of phi xx. Because remember, Z was U triple X. The coefficient of my phi x, which is my, that's my, oh yeah, I should say phi is your infinitesimal. D phi by dx is the infinitesimal for ux. And the double derivative of phi is my infinitesimal for u double x. And that's the formula that you have for the infinitesimals. And but you can see that they're exactly the same. And what that means is, of course, that so here's my beautiful formula. The conservation law is linear. It's just the inner product of the conjugate variables with the infinitesimals, which is kind of very striking. And I talked to various people and they hadn't seen it, but I kind of can't believe that it's not known. But anyway, we can enjoy it today. I enjoyed it. It's not hard to prove that it's not hard to prove that the coefficients of the differentiated infinitesimals are the same as the lambda I, because they satisfy the same recurrence relation and they have the same starting point. So that's the proof. The proof is very short, actually. When you actually look at it all and work it all out, it turns out that it's exactly the same. Okay, so what now? If I write these conservation laws in matrix form, I get, of course, my matrix of infinitesimals that I showed you before, and times this vector here of the PU and the PV, because they're all linear. And this effectively is a moment map. I find anything with a star on it, I don't know, I'm an antipodal person, and I find these things, I feel like I'm in a hall of mirrors as soon as somebody puts a co on it or a star, but you can do it. This is effectively a moment map. So let's just prove that the equivariance, so the moment map has a famous equivariance with respect to the adjoint action. So let's just prove it and just see how this gorgeous formula gives it to you kind of exactly. So the Hamiltonian is this. Oh, what am I doing? Oh, I guess I'm doing something else first, sorry. This is the Hamiltonian, this is the definition of the Hamiltonian, and when you write it in terms of the new variables, it looks like this. This is also invariant under the group action. Oh, yes. In order to get the group action on my conservation laws, I have to give you the induced group action on my conjugate variables. And so it's easy to see it using this way. So here's the Hamiltonian. It's invariant under the group action. If I look at the, so these are my conjugate variables. It's very easy to see when I put it into the term of the original u double x, u triple x, it's very easy to see that it transforms linearly, and that this matrix is the Jacobian of the transformation. So that's kind of semi-trivial to show that. And then it's then not hard to see that the conjugate variables transform by the inverse transpose. This is very easy to see, so obviously your action on your whole space has to be symplectic, and for any A in GL, and you get that this is NSPN actually. So this gives you the induced action on the conjugate variables, and now it's easy to see the equivariance of this moment map mu. Basically, all it is phi, the matrix of infinitesimals, times this vector of conjugate variables. I simply, to get the G dot, and I put a G dot on everything. So here, this omega I get this matrix here, just depends only on the group parameters. It's the adjoint representation times the original thing times A transpose. That's coming from here. And of course, the P's go as A inverse transpose. They cancel, and there it is. So how gorgeous is that? So that's really nice. So it's, yeah. And you get rather, it's trivial to prove these properties from the exact formula. And so in terms of the Poisson, the standard Poisson bracket. Okay, so let's move to discrete problems. And here we have this gorgeous thing which Peter Hyde and I spent a long time working on. We've written how many journal pages on discrete variational methods, and it all comes down to one very key thing that you notice. And there's a reason for what I'm going to show you. So here it is. So here's my discrete Lagrangian that depends on un plus 1, un plus 2. So I'm just going to look at the simplest case with one dependent variable and one lattice point. So it's exactly the same process. You just put a un plus epsilon vn. The variation on un plus 1 is vn plus 1. And so I get this fresh A derivative. And now, this is the analog of integration by parts. I'm simply going to add and subtract. I'll show you on the board in a minute. But what happens, I'll do it on the board now. Let's see now. So this is integration by parts with derivatives, and it's because, and so basically we think of this as an L2 inner product, and the adjoint of d by dx is minus d by dx. So now let's look at what we're doing for the discrete. For the discrete, can you read if it's this low down? Yeah? I have fn gn plus 1 is equal to minus 1 gn plus the identity minus the shift inverse of fn gn plus 1. You just kind of add and subtract. Now if you look at this, this is my total derivative. It's the total shift. And what I have is a little L2 in a product. And what I have is that the adjoint of the shift operator is the inverse shift. So you can see that the operation of systematic integration by parts is operating via a very particular mechanism which algebraically, which you can view as the same thing. So that's why with these we have the formulae are identical with this symbolic shift. So the jth derivative becomes the jth shift, and minus d by dx becomes the inverse shift. And you can then just take all those fancy formulae and rewrite them, and you will get the correct result obtained like this. All right. So we get the equivalent formula for the moment map with exactly the same proof. So to keep things short, we do the same trick. We write our jth order Lagrangian using these Lagrange multipliers, introducing new variables. We now get a very similar kind of thing with a similar kind of recurrence relation, but it's what's that great Latin phrase? Mutatis mutandum. It's mutatis mutandum. So we lose some minus signs here because we're not introducing a minus sign with our adjoint of d by dx. So we get a recurrence relation for our conjugates, and the generating function of the corresponding symplectic mapping is this. So this is what I'm not allowed to call a Hamiltonian, a discrete Hamiltonian. It generates it's a generating function for a symplectic mapping. I'll show you what that is on the next slide. So these are the Euler-Lagrange equations, and here it is. So now I get the difference on the u's is dh by d lambdas. Remember, lambdas are my conjugate variables. But now I get this kind of inverse shift. It's the negative derivative with respect to my UNs. So this is what it looks like, and it's really quite different in that you get a negative shift here on your conjugate variables. So this is the one kind of big difference. All right. So let's now look at Lie group actions on my discrete Lagrangian. So the only key point here is I have a Lie group that depends only on the dependent variables, and the action on un plus 1 is the shift of the action on un. And this gives you everything. So this is the analog of the prolonged action. And that means that the infinitesimals work like this. The shift of the infinitesimal on the jth derivative is the jth shift of the infinitesimal on un. And using this formulae, I can obtain the exact analogous conserved quantities using this beautiful linear formula. I have now my matrix of infinitesimals times my vector of conjugate variables, and my induced group action, as before on the conjugate variables, is the inverse transpose of the conjugate of the Jacobian of the transformation, like that. And with this, I now obtain results analogous to this using the standard Poisson bracket, the standard symplectic discrete Poisson bracket. But that seems to be the end of the analogous results for these discrete symplectic mappings. So there's three things, and each one, to my mind, is worse than the previous. So before, within the smooth case, the corresponding Hamiltonian was also invariant. But this is now false. Pardon? We don't have time as a continuous variable, but even for autonomous systems, I mean, even where you're not really using time overtly, we still don't have it. So so even in the simplest case, what you find is that the induced group action on this generating function is essentially second order. And you never get this in the smooth case. Only second order terms can transform with second order infinitesimals. And yet if you're looking at the mean value theorem, this is a second derivative of phi. So that's really very, very different. It's not constants on solutions of the Euler-Lagrange equation. So it's not a conserved quantity. And this is because you don't have a continuous time. This is the one that fails because n is no longer a continuous variable. On solutions of the Euler-Lagrange equations for this variational problem, the solutions are cubic in n, but this generating function h is linear in n on solutions. So it's not conserved. But the third one is the worst. Null Lagrangians give rise to non-null symplectic mappings. So let's take a null. So this one, the Euler-Lagrange equation is 0 equals 0. That's because it's a total derivative, a total difference. So when I do a sum, I get a telescoping sum. The sum only depends on the endpoint, so the variation is null. It's the same as in the smooth case. So if I write L in terms of my conjugate variable, Lagrange multiply, and I write down the generating function for this corresponding symplectic mapping, then the equations are essentially free. un plus 1 is the shift of un. I mean, anything is a solution, right? But on the solutions, my generating function looks like that. So I'm really getting something for nothing. And you cannot do this in the smooth case. If I have a purely null Lagrangian, you cannot even form the Hamiltonian because it's linear. It's going to be linear in the highest order derivative. And to form the Lagrangian, to do that conjugate variable process, you need to have at least quadratic.
Is this saying that there is no conservation of energy in the discrete case?
Well,
Convolutional principle, there is no.
you don't. I'll show you another slide further on where you can build it in if you have to have it. Okay, so adding null terms is how you incorporate boundary conditions. So you want your boundary conditions to come out as the natural boundary conditions of your variational problem, and you build that in with a null Lagrangian, adding a null term. So I thought for a while about fiddling with the null part of the Lagrangian to get the conservation, but I decided then you shouldn't do that. That the null part of the Lagrangian was part of your application. So how to obtain conservation of H? Well, if you look very carefully at Noether's theorem for smooth systems where time is a continuous variable, the reason is because when you do the chain rule on UX and you reparameterize time, you cannot separate out the variation on time from the variation on U. And that's why it works. That's actually the algebra of how you get conservation of energy. So you can copy that. If you have to have, if you've got a physical problem and you have to build in conservation of energy, then you can do it in this kind of artificial way. So you remember your variation on U and your variation on time can't be separated. So you can do it in this, if you take this very artificial thing, and then this of course is the analog of your dt in your one form, in your integrand. And then if you build it, if you construct your Lagrangian to be invariant and to look like this, then you will get H is conserved using this mechanism. So option B is so this is highly speculative. This is just, we're practically to the wine, right? So shark-infested waters. Now remember, the analog of the variational process that I showed you was really only on the continuous variables, the U's, which can vary continuously. And we got all of those results, but they are all effectively a local variational process. So the idea is, and I've looked at quite a few ideas, and I have no conclusions. I only throw this at the audience. is to actually have a bona fide non-local variation. Because remember, n is not a local variable. It's just really not. So if I multiply my L of n by dn, whatever that is, so this is now make-believe symbolic computation. We're swimming. I prefer dolphins to sharks. But anyway, by dn, this is now going to be my variation on my, so this delta means my variation on my un, and I'm going to insist on this shift rule that it commutes with the shift. And this is kind of like dx. You know, dx here and dx there is the same form. Yeah? So that's kind of like my dx. But like a weak derivative, my variation on this, and this is also in the formula for obtaining the Hamiltonian from the smooth case, is you vary that dt. This is what you're doing. So now my variation on my dn can only be known via its action under the sum operator like this. And so this is almost like a weak derivative. So this is a non-local variation acting like a weak derivative. And the only reason I'm doing this is because it works. So if I now do this on my Lagrangian here, and I do my delta in the usual way, I get my Euler-Lagrange equations here, and then I get this like that. And that is more or less modulo an interpretation of this delta, is my generating function for my Hamiltonian. Now, what does it mean? Here's the big problem. H is not conserved. To my mind, there's terms missing. So how do you build in extra terms? So there's two big theories that give you extra terms. One of them is stochastic calculus, so Ito's lemma, where the variation on dn also has a dun on it. A quadratic d. Actually, if you vary it, you get a second order term, and that kind of would fit in with the fact that the invariance was second order, the lack of symmetry was a second order effect. The other one is to use non-commuting variables, and you can obtain the very equivalent formulae to the stochastic calculus in the famous cases, you know, the Brownian motion case. You can obtain those using non-commuting variables. I haven't yet made up my mind. I simply throw this out as a discussion point, and this is what I read en route. So this is our main paper with Peter Hayden, where we actually explore this analog to the nth, and we get an enormous set of results out of this analog here. And Peter Hayden's latest paper on multisymplectic structures. This is a very nice review paper in Acta Mathematica on symplectic mappings, and this is what I'm halfway through on the stochastic calculus. So anyway, I hope you found it interesting, and okay, pre-wine talk. Thank you.
Are there any questions?
Really silly one. I see I'm toppling Martha over. She's toppling over. In your work with Tanya Gonsalves, you said there was some differential operator that began with dq. It looked very much like the second KDB operator.
Yes, that's exactly what it is. Yes.
It's because of the Schwarzian, right?
That's right. So exactly what it is that this is the differential invariant for the t derivatives, and then v was the Schwarzian derivative. Minus stuff. And so now this is like Eveline's talk. We have one t derivative here, 3 x derivatives here. If I differentiate this 3 times with respect to x, differentiate that once with respect to t, you get error terms. The error terms come out exactly as she has, and so you can do this calculation using moving frame technology. And indeed, you get that. I have to get this right away now. You get that exact operator that I showed acting on W is d by dt of v. So this is the syzygy on the differential invariance, and this is where the operator comes from. And so when you do the variational process, this t, if you just swap that for epsilon, which is how I'm doing my Frechet derivatives, then you see where this operator comes from. Like that. Yeah.
Just racking my brain how you could do something like that for KP or something, but you would have to find a group symmetry, right? Instead of SL2, you would have to.
Yeah, you know, I develop algorithms, and the problem with integrable systems is everything is magic, and also everybody knows the results. So I tend to stay away.
So you just killed my question. I had a question,
No,
but
no,
I decided that I'll skip it.
So actually in my book, I find the syzygies relevant to Sawada-Kotero, and in my paper with Peter van der Kamp, we find the ones suitable for vortex filament and other examples. So I have actually worked on those examples, but I try not to use them as integrable systems as see, it's too easy when you know the answer to direct your algorithm. When you know to direct your algorithm, you have to. When you're developing algorithms, you have to stay away from ones. I know Willie was saying he wants the ones where the answer exists, but you don't necessarily have to know what it is, right?
They can give you the cases you don't know the answers for.
Well, I'm just saying when you're working on algorithmic things, you have to be very careful that you're not building in the fact that you know how to derive the result from the particular example you're working on. Yeah. But clearly, those syzygies are these famous differential invariants coming out of differential geometry and integrable systems. There's a huge amount there that's known.
Any other questions?
So in the parametric study of parametric equations, Manifest Okamoto Hamiltonian plays an important role, even though the Okamoto Hamiltonian depends time.
Yes.
How do you think about some construct Lagrangian or Hamiltonian with some difference boundary?
Yeah, that's right. So I think that, so one of the things I did with Peter Heiden was that we actually using what's called homotopy formulas coming out of the variational calculus, you can actually write down Lagrangians. If you can obtain the Lagrangian if you know that your equation, is an Euler Lagrange equation, you can write down the Lagrangian. You can do that algorithmically. So we did this for some of the discrete Painlevé equations. Yeah. So there's I mean, obviously, you're getting into the inverse problem of calculus variations. If you have a system, then you have problems. But if you know that your system is an Euler Lagrange system exactly as given, as opposed to a few coordinate transformations away, then you can write down the Lagrangian. Yeah.
Oh, thank you.
Any more? If not, let's thank the speaker again.